All right, so when we look at these acid-base definitions, as of today, we have 2 definitions of acids and bases, and then by the end of the next week, we will have a 3rd one, right? So if we look back in 111, what was the first way we can determine an acid or a base? Let's talk about the definition of an acid. What is the definition of an acid? Anybody? Anybody have a definition of an acid?
A substance that donates a proton.
So we can look at something that donates a proton. So if it donates a proton, which I'm going to call the H+, that is the Bronsted-Lowry definition of a acid, right? If it donates a proton, this H+. If we look at the Arrhenius definition, it says an acid in water forms H3O, right? This is the Arrhenius definition, right? Both of them are going to be similar. This one specifically indicates that this solution has to be water, right? In here, we're only worrying about how the molecule itself changes. So going from here to here, we become less specific, right? And the third definition, which we'll learn later, doesn't talk about the proton, but actually talks about the electron. So our Lewis definition, which we'll learn about later, says that we accept a pair of electrons, right? This is the Lewis definition, right? Which is consistent, excuse me, with everything else we've talked about Lewis things, right there. We're always talking about presence, locations of electrons. In this Lewis definition, we're accepting a pair of electrons. We're gaining a pair of electrons. In each one of these cases, though, the definition becomes less specific or more general. Let's use that term. Right? So we are putting less and less constraints on what we can define as an acid or a base. Okay? And we will see, we'll have then, if once we define an acid or a base, we're going to sort of define the strength of these acids or bases as being either a strong acid or a weak, strong base, or a weak acid and weak base, right? So once we identify them, then we're going to classify them. Right? So if we look at this reaction here, we want to identify the Bronsted-Lowry acid, the Bronsted-Lowry base, and the conjugate. Right? So I'm going to rewrite this equation down here. We had HNO3 aqueous plus water, which is a liquid, forms H3O plus, which is aqueous, and NO3 minus, which is aqueous, right? And if we look at the definitions, right, if we were in water, so this is going to be our Arrhenius acid, right? If we look at the Bronsted-Lowry definition, we're looking to donate an H+. So this H+ here is being donated to the water. So that makes this our Bronsted-Lowry acid. If the donating makes it an acid, the accepting that makes this the base, right? Which means that over here we have some sort of a conjugate, right? So when we define acid or base, it's always in the direction the reaction is written. The reactants are always acids and bases. The products are always going to be the conjugate. And in order to determine what it is, we have to take this reaction and go back in this direction. Right now, in this direction, this extra hydrogen is going to be donated back to that. So that makes this the conjugate acid and makes this one the conjugate base. That makes sense. So acid and base we define in going in the as written. The conjugates we define in the reverse, and we just add the word conjugate in front. Okay, makes sense. Questions on that? All right. Now, so once we've now defined this acids and base, the other thing we have to ask ourselves is this a strong acid or base? Right? And in order to do that, we unfortunately have to memorize a list of strong acids and bases. So what is the list that I gave you in the lecture of strong acids? Is it this lecture that I gave you? Have I given you a list of strong acids in the lecture? All right. So we know that the strong acids, whether I gave it to you or not, are going to be things like nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. The first deprotonation that's not how you say. The first loss of hydrogen for sulfuric acid, and the other one that we gave you was HClO4, I believe. Right? All of them are either these halogens or where the difference between these two values is greater or 2 or greater. Right? Those are strong. And what does it mean to be a strong acid? All of these means that these completely dissociate, right? So these are actually no equilibrium. So this reaction doesn't go in both directions. It only goes in the single direction to the products because nitric acid is a strong acid. Okay. So now, if we find the pH to be 1.5, let's calculate the POH, the H plus, H3O plus, and the OH minus, as well as the original HNO3 concentration. Right? So we can go back then, and we've defined the pH as 1.45. Jeez, right. But if we remember that pH is equal to the negative log of the H3O plus concentration, right? So if we know the pH, we can calculate the H3O plus concentration, right? Because the H3O plus concentration is equal to 10 to the negative pH. So this is equal to 10 to the negative 1.45, if I can remember that number right. And when we do that, remember how to use the calculator. We get a concentration of 0.035. Leave it there. Right. Molar for the H3O plus concentration, right? If we remember the definition of pH, or if we look at how water reacts, let's look at that, right? It can break into H plus, H3O plus, and OH minus. Wrong parentheses. Right? This is referred to as the auto dissociation of water. Two water molecules can react to form the H plus and the OH. This equilibrium, as we call Kw, has a value of 1 times 10 to the negative 14th at 25 degrees Celsius. Right? But it also means that because of this auto dissociation of water, if this value goes up, this value has to go down, right? So we can use this Kw, right? Because Kw is equal to the concentration of H3O plus times the concentration of OH minus. If we have one of them, we can calculate the other, right? So if we want the OH minus concentration, that's going to be 1.0 times 10 to the negative 14th divided by our H3O plus concentration. So this would be equal to 2.81 times 10 to the negative 13. Just call it 2.8 molar. All right. So now we have the H3O plus concentration, the OH minus concentration. The last thing we needed is the pH. Or POH. If pH is equal to the negative log of this, we can say that the POH is equal to the negative log of the OH minus concentration. Or we can say that pH plus POH is equal to 14, right? Because of this. Either way, when you do that, the POH is going to be equal to 12.55. Questions on any of that so far? Right. Either way, either equation you use, you're going to get that same value. All right. So if we go back to what else we need to solve for. All right. So we got the POH, we got the H3O plus, we got the OH minus. Now we need this original H3O plus. That's where this comes, because this is a strong acid and it completely dissociates. The amount of H3O plus has to be equal to the H3O plus concentration is going to be equal to the original acid concentration. So if this is, so the HNO3 concentration has to be equal to the 0.35 molar because it completely dissociated. And it's a strong acid. If it was a weak acid, then we would have to solve a weak acid problem, which we will talk about on Thursday because we care. Okay. So in this activity, or in this lecture, we are doing essentially three things. We are learning how to define these acids and bases. We are learning how to calculate pHs from concentrations of H3O plus or H plus. And we are learning to convert between H3O plus and OH minus, and conversely the POH. And all three, that's going to be the foundation of what we do when we move away from strong acids to talk about weak acids or weak bases in the coming class periods. All right. Any questions about any of that?